during the time that I was a postdoc, I actually switched my research focus, thinking less about speculative ideas beyond the standard model and thinking more about the structure of the standard model of particle physics itself. And I've gone through another transition to thinking about the way we can incorporate machine learning into particle physics. And that's what I want to tell you about today. So the Centaur, as many of you know, is a mythical creature that is half human and half beast. And that's maybe the way you can think about particle physics and machine learning. And I allow you to think about which part is the human part and which part is the beast part. I've been giving a number of talks with this title. And my colleague, Kyle Kramer, who's a leader also at this intersection, pointed me to this fantastic New Yorker cartoon of the Centaur scale. One of the things that I've been trying to figure out is, what does it mean to have the right amount of horse? What is the right balance between thinking about fundamental physics and thinking about machine learning developments? And also thinking about this talk here, this talk is going to be some kind of hybrid between almost like high-level colloquium stuff and then more technical things for the particle physicists friends I see in the audience. But the theme is going to be trying to find this balance. And you'll see how I've done this through 2 different research projects that I've done over the past year. As mentioned, I'm the director of this AI Institute, which is also trying to, again, find this balance. While there are some people who think that, machines will take over, and some people who think that we need to stick to our core competencies in the fundamental physics, I think that actually the synergy of those 2 things is the way to go. And this synergy was, of course, highlighted last year with the recognition of this kind of intersection of AI and physics, the idea that you could have learning, which oftentimes we think about in the language of human cognition, but learning can happen through dynamical systems. And that statistical reasoning is a way of confronting mysteries of the universe. And of course, the idea that AI and these algorithms more generally broad implications for scientific discovery. And so in particular, we're actually going to see Boltzmann machines, which of course he got the Nobel Prize for, appearing later on in this talk. And you'll see how a concept that is actually quite old in Boltzmann mechanics actually has some implications for the way that I think about particle physics data sets. Okay, so the top level messaging that I've learned over the past, however many years from this collision of high energy physics and machine learning is, first, to meet the standards of scientific rigor and performance, we need to teach machines to think like a physicist. And part of my skepticism before getting into this field was my frustration with machine learning algorithms not actually having core principles built in, core principles like, for example, the symmetry structure of space and time. And so the first example that I'm going to be giving is actually teaching a machine to understand space-time symmetries. And you'll see how a physicist thinks about building equivariant machine learning architectures. At the same time, I've had to admit that to fully capitalize on AI technologies, we also have to teach physicists to think like a machine. And this is something that I've been quite, again, reluctant to, that if I think about the way that I perform calculations, I don't usually think about it in the language of optimization or brute force search, or thinking about algorithmic reasoning, or worrying about the computational complexity of the software that I write. But actually, this seems to be kind of a muse for me, actually. Thinking about the way a machine might solve a problem turns out to be really relevant for thinking about how we can solve that scientific problem, not just in a more efficient way, but also in a way that gives insights. And so this is what I think about this power of Centaur Science, of really doing these things at the same time. And this idea is definitely not new. There's always been a link, long time been a link between progress in computation and information theory and progress in the physical sciences. We already talked about statistical mechanics, Boltzmann machines, the connection between information theory and maximum entropy solutions. That's a key connection. Also quantum computing, whether or not you actually build a quantum computer, thinking about the way you would do computation in the quantum context gives us new insights into things like computational complexity. So I'm not the only person advocating for the Centaur Science approach, and I think a lot of you in this room are eager to merge together domain knowledge from one area together with more general advances in mathematics, statistics, and computation. Okay, so for this talk, there's going to be 2 case studies. I'll start off with just a particle physics 101 for the non-particle physicists in the audience, and trying to just explain that what we do is decipher collision debris, and that requires statistical inference, and inference is well matched to the Centaur scientist approach. Then I'll explain to you 2 relatively recent research projects. One about giving transformers a boost here referring to Lorentz boosts, which is what happens when you take particles and accelerate them to relativistic speeds, and the symmetries of space-time, and how you can teach a machine to think like a physicist by baking known symmetries into machine learning architectures. And it's a very interesting connection between physics things that are in my brain and how you actually turn that into a computational structure. And then rounding things out with QCD theory meets information theory. So QCD, quantum chromodynamics, this is the description of the strong nuclear force. And actually thinking like a machine as a way of tackling the challenge of doing certain QCD calculations, turning that into a more generic optimization problem. And for the particle physicists in the room, for this last part of the talk, I will give you a full seminar at the Bay Area Particle Theory seminar tomorrow on just this element. So if you want more of the technical details, you can come to my talk tomorrow. Okay, so let's dive in just into some particle physics 101, and just reminding you that that inference is a real important strategy for deciphering particle physics data. So this is the standard model of particle physics written in pinwheel form. These are the fundamental ingredients of the standard model: the quarks in orange, the leptons in green, the force carriers of the standard model in blue, and the Higgs boson at the center of the standard model in purple. And when you draw a picture like this, you might get the impression that, oh, these are particles that you would hold in your hand, that you can actually see these directly, and that you could, for example, do a classification problem of saying, is this object one of these elements of the standard model? Unfortunately, we don't actually see these things directly. The only particles that directly interact with us are those that carry electromagnetic interactions, so photons, electrons, and muons. The ones that carry E&M interactions, those are ones that we really can, in some sense, hold in our hand, if you'd like. But all the other particles in the standard model, their properties and their existence even has to be inferred through other means. So my specialty is in the strong nuclear force, and the strong force famously confines, such that if I take quarks and gluons, I can't see them in isolation. They form bound states. Those bound states are composites like pions, kaons, protons, and neutrons, which are maybe the more familiar ones. So from these bound states, I somehow have to infer that quarks and gluons are really fundamental ingredients. And then some of the heavier particles in the standard model, top quarks, W and Z bosons, Higgs bosons, these are particles that disintegrate before you have a chance to touch them, if you'd like. And so those ones you can only infer from their decay products. And then neutrinos are particularly frustrating because they just sail right through your detectors, so you just infer them by their absence in a collider event. And if this were the end of the story, this would be relatively straightforward, but we don't even get to see those particles coming out with those names. What you actually see in a collider are hits in tracking electromagnetic and hadronic calorimetry muon systems. Somehow you have to figure out what type of particle you got from the different hits that you get in the sensor. These sensors fire every 25 nanoseconds because that's the collision rate that you have at the LHC. So you have to do a fast inference to figure out what's going on at 40 megahertz. And then there's various machine learning and also more traditional analysis techniques to decipher this collision debris. So my specialty are in these collimated sprays of particles that are called jets, which are represented here by these yellow cones. And these are sprays of particles that had their origin, at least as far as my theory calculation is concerned, their origin as quarks and gluons fundamentally. But because the strong force confines, their manifestation are in 5, 10, 20 particles streaming out. And somehow I have to figure out whether a particular spray of particles is that more likely to be a quark or more likely to be a gluon or some more exotic object. And that's why inference is so important in the particle physics context. And so, even before I got excited about machine learning, I got excited about these things. These are these jets, these collimated sprays of particles. I have old slide decks from when I was a postdoc at Berkeley, really excited and enthusiastic about these sprays. These are my friends. And for some reason, I've continued to stay friends with them for 15 years. And again, jets are manifestations of underlying quarks and gluons, but you can't see them directly. And one jet basically carries no information by itself. That actually, any individual jet, the misclassification probability is very high. It's only through inference that you can even tell kind of what the proportion of quarks and gluons that you have is. And so statistics, inference, these are things that I, of course, knew about when I was a postdoc here. But then you're bringing machine learning into the game to do more powerful inference on what's going on in collision debris. Okay, so that's the Particle Physics 101 complete whirlwind. what's the machine learning 101 for the physicists who are in the audience who might be scared of machine learning? And so the machine learning 101 is to say, well, if I want to do inference, let's say I want to tell the difference between quarks and gluons, well, how would I actually do that with machine learning? And kind of what is the basic technique that we would do for basic inference in a particle physics context? So the machine learning 101 is simulation-based inference. And this is a collection of tools that we use to take simulations of, in our case, collision debris, and turn that into our best guess of what's actually going on fundamentally. And this technique, the likelihood ratio technique, is a likelihood ratio trick, is a trick that's in kind of, a embarrassingly large fraction of my papers are based on using this trick. A lot of high energy physics problems can be expressed in this form. But it's a way of taking simulation information and then turning into things that have statistical meaning. So if I want to say, is this particular spray of particles, is it more likely a quark or a gluon or some other exotic object? Basically, I have a probability distribution of some features in that jet. Let's say P is gluons and Q is quarks. And if I want to do inference about whether it's more likely to be quarks or gluons, then I want to calculate the ratio of P of X over Q of X. But I don't have pencil and paper answers for what P of X over Q of X is. I just have finite samples drawn from those distributions. So I have finite samples, capital P and capital Q. But if you give me a learnable function f, parameterized in some flexible way, and we'll talk about different flexibilities in a moment, then I can compute a loss function or loss functional. And if I average over the logarithm of f over sample p, average over f minus 1 for sample q, and I float the parameters of that function f to try to minimize this object, I get something that I can then use as an approximation to something that I could use for statistical inference. And in particular, just trust me for a second, asymptotically, meaning if the f are infinitely flexible and if I had infinite training data, then the value that minimizes this, it should not be obvious to you. The value that minimizes it is the likelihood ratio P over Q and its asymptotic limit. So I've succeeded at turning simulations into some function that I can use for downstream analysis. And the actual value that I get of the minimum has statistical meaning. It's the Hilbert-Leiber divergence. And you can then imagine, if I use machine learning, the neural networks, and optimization through some kind of stochastic gradient descent to figure out these things, this is a useful object that I can use for inference tasks. Yes?
Can you remind me what Hilbert-Leiber, does that have some...
The KL divergence is also known as the relative entropy. Okay. So P log P, that's Shannon entropy. But if I now have continuous distributions, Shannon entropy is infinite. And so you have to set a baseline entropy with respect to what? Entropy with respect to Q. That's what KL divergence is. Okay, so for the particle physicists in the audience, this is probably, for anyone who's doing stats, this is very familiar. Anyone who's doing particle physics is like, geez, how the heck do you do this? But actually for particle physicists, think about L not as a loss function, think about L as a Lagrangian, and take every time you see an expectation value and turn it into an integral. And then to a particle physicist, this is just Lagrangian mechanics, okay? Where we replace the time variable with the features x. Our Lagrangian is just P log F, Q, F minus 1. And then we can instantly, in our heads, do the Euler-Lagrange equation by varying the Lagrangian with respect to F, set that equal to 0. For the non-particle physicist, this is just the analog of F equals ma that you would have learned in a freshman mechanics course. This is the generalization of F equals ma. Only in this case, we're doing in some asymptotic limit where my acceleration is 0. And the solution to this, take a derivative with respect to F, derivative with respect to F, solve for F. Maybe you can do it in your head. The solution is P over Q. And so this requires a shift of your focus from solving problems to specifying them. And then also remembering that every time I have this integral over dx, integral over features, really secretly, I have to go back to this and say, I really have stochastic samples. But once you have that connection, it's actually pretty straightforward to build loss functions that are useful for various particle physics tasks and let the machine find optimal solutions. So that's the machine learning 101. And once I saw examples like this and actually saw that I myself could construct loss functions that were useful for the tasks at hand, not just for classification, but for other types of purposes, kind of generalizations of this, I was off to the races. And I went from being an AI curmudgeon, complaining to my friends who were doing machine learning that you're not doing physics, to saying actually now the only way anyone should be doing physics these days is with machine learning. So becoming an AI evangelist, I became director of this Institute for Artificial Intelligence and Fundamental Interactions. I had embarrassing quotes in the New York Times when Dennis Overby asked me, could a computer devise a theory of everything? And I very enthusiastically said, yes, in 5 to 10 years, of course, we're going to be able to do this. And my friends at the time in 2020 kind of were saying, Jesse, you've gone completely off the deep end. No way could you ever have a machine, devise a theory of everything. 2 years later, you had the release of ChatGPT, and then you saw actually computers could do pretty sophisticated reasoning. And then people were maybe going in the other direction, saying it's only a matter of time before the answer to life, the universe, and everything was going to come from some type of foundation model. And now in 2025, I've been having some fun playing around with the various new reasoning models to try to ask this type of question. And it's quite interesting, kind of that dialogue that you can have with a machine. But when it comes to particle physics and this kind of Centaur Science approach that I'm going to tell you about, the way that these things manifest is not in this kind of sci-fi version of the machine telling us what to do. What it manifests in terms of the research that I'm doing are plots that look very familiar to a particle physics audience, but behind the scenes actually has some really sophisticated machine learning backing it. So my collaborator, Radha Basandra, is in the audience here, along with Ben Nachman, who I think is on Zoom, and my student, Rikov Gambir. We did a Centaur Science analysis, searching for new phenomena, really old phenomena that are well known, but in a new region of phase space, using a combination of machine learning-based strategies and then very traditional particle physics techniques. And you kind of needed both in order to do the analysis that you wanted to do. So in this particular case, you're looking for a bound state of a bottom quark and an anti-bottom quark bound together, but you're trying to find that bound state in a region of phase space that had never been explored before. It turns out that this bound state, it's called an upsilon, it decays to muon and an anti-muon. And if you take that muon and anti-muon and put them together, what you find is a distribution that has absolutely no structure to it. You can't see this, what we call a resonant feature. But if you divide up your region of phase space into a kind of a control region, a sideband region on either side, and you train a normalizing flow to interpolate through what we call the signal region, and then you use this likelihood ratio trick that I just taught you about to do a classification of, is it more likely to come from this interpolation of the background versus a candid new signal? In fact, just if there's anything in the signal region itself, what you can do is get a classifier that you can place cuts on and actually expose not just one, but a sequence of 3 upsilon resonances. Okay, so the top line here, background predictions using normalizing flows. We're using a relatively shallow machine learning technique of boosted decision trees to do this classification of signal region versus background region. So that's the one half of the Centaur. The other half of the Centaur is then recognizing the domain knowledge from physics, which is that if you're going to estimate the statistical significance for this structure, you have to know something about the resolution of your experiment, what you actually think the background model might be, basically physics domain knowledge, that we have localized resonance and kind of how localized it is. And that allows us to then set, well, in this case, the p-values show we've seen something. We see that, approaching 5, 6 sigma, that you can actually see these resonances in a place that you wouldn't have been able to see it without using something like a machine learning-based technique. And then the fact that this likelihood ratio has a statistical meaning, you can turn that into an even more optimal analysis, where instead of what a particle physicist do would be doing cuts, you can actually do something where you just do the inference problem directly. What's the probability that I actually have seen something that deviates from the background model by itself, and actually doing this likelihood ratio trick, turning it into likelihood reweighting to actually get an even stronger significance by using all the information that the machine had recovered. Right? So this is what it looks like. It doesn't look like the machine telling me this is the answer. Yes, these upsilons there. It's really a combination of physics knowledge plus things like the simulation-based inference. That's the way that this has manifested in my own results. Yep. So, okay, this is this rise of Centaur scientists who synthesize physics intelligence and artificial intelligence. And now I want to give you 2 more examples from my research about what this looks like in practice. So we'll start off by teaching a machine to think like a physicist and incorporate domain knowledge from our field. So just to reiterate what I said before, the LHC analysis pipeline is based on simulation-based inference, where you compare real data to synthetic data, And that comparison is what you use to, for example, make a discovery of something new. This is made possible by the availability of vast data sets and trustable simulations, and it's only possible because you actually can do these simulations that you actually have a chance of making correct inferences. And people have been doing this in the context of shallow machine learning for many, many decades. What machine learning is adding is high dimensional statistics as a tool that we can use for discovery. So I've already mentioned this already, but this is kind of what's coming in on the high energy physics side is this pipeline. What's coming in from the machine learning side is the shocking ability of transformers to process information in a way that I'm not sure that I fully understand why it's working. And when I talk to experts, it's also maybe not so clear. Maybe you can understand, someone can explain to me why transformers scale so well. But the thing that I'm going to focus on in this talk about what transformers are doing is that they incorporate multiplication as a primary operation. And we'll see what that has to do with particle physics in a moment. So if I go back to that likelihood ratio trick, I have a flexible function f that I'm going to float around in order to learn something useful. Every neural network is just a fancy version of function approximation. Standard feed-forward networks are based on linear transformations and nonlinear activations. Doesn't really have multiplication as a primary operation. But what transformers have is it does have multiplication as a primary operation, inspired by the multiplication you would do if you had a visual scene, if you wanted to mask out regions of that scene to not pay attention to. You multiply by 0 to mask out things that you don't care about. That's called attention in that literature. And a particular type of attention mechanism that transformers use is dot product attention. And dot product attention works well, scales incredibly well empirically. Again, not really sure why it works so well. But maybe the thing to emphasize is that in terms of primitive operations, this attention mechanism has things like matrix multiplications inside of it. And whether that itself is really the engine that drives things, that will be the thesis of this talk. And just to mention work that also my student Rick did on alternative ways of doing multiplication that don't use attention, but are kind of inspired maybe by it a little bit. And those also tend to do better empirically in our particle physics problems. But here we're going to focus on transformers and ask, can we take transformers and adapt it to a particle physics context? So one thing you can definitely do is take a transformer and adapt it to a particle physicist. So as an April Fool's joke in April of 2023, some troublemakers at IFI created not ChatGPT, but ChatJSCT. And ChatJSCT is very enthusiastic about particle physics, uses probably the same number of exclamation points as I'm using in this talk right now. If only a transformer could decode the mysteries of the universe as easily as they decode language. Sounds eerily like myself. You can use transformers not just to mimic myself, but also mimic maybe more famous scientists. And so as a public engagement event for IFI, building a version of this that mimics Marie Curie, who has some interesting words about why it's important to fund AI in science, even though she herself did not know anything about AI. In fact, she prompt engineered this to not know anything about AI. She says, which is very poignant to this moment, funding science is not just an investment in knowledge, but also an investment in the future of humanity. And maybe that message might make its way over to Washington, D.C. someday. But transformers have this incredible ability to process, in this case, textual information. And you can also use it to process visual information. And as one use of transformers that has nothing to do with particle physics, I worked with an IFI fellow, Siddharth Mishra Sharma, and a high school student at the time, Yiding Song, to use transformers to correlate information, textual and image information from a catalog of Hubble images. So what you're going to do here is you're going to try to do what's called contrastive language image pre-training. So you're going to try to take text and embed it in some high dimensional space, some Rn, take images, embed it in that same space, and then contrastive learning is trying to put text and image that came from the same origin, put those close together, and text and image that are coming from different origins, put them far apart. But again, you have a text transformer that encodes things into the space, an image transformer that encodes images into that same space, try to push them close together, push them far apart if they're coming from a different place. And then you get this embedding where in this space, you can now correlate text in this region of this high dimensional space is associated with particular images in that region of high dimensional space if their underlying science is the same. The particular example that we're using here is using a database of abstracts that used to justify pointing the Hubble telescope at a particular part of the sky with the actual images that were taken later. So this correlation is noisy, since sometimes you point the telescope at a part of the sky and don't see what you expected to see. But the correlation is good enough that it does better than off-the-shelf models that are trained just on internet images. So for example, here is an image of a ring. For physicists, you say, oh, that's a ring. I know what a ring is. That could be some gravitational lens where you have some foreground object that's lensing light from a background object. That looks like a gravitational lens. That's what I, as a particle physicist, would say, since I don't know astronomy. And that's indeed what an off-the-shelf transformer-based system would say. And that is very incorrect for any of the astronomers. Very incorrect, but this procedure that Sid Yiding and I did gets a better answer. It actually correctly identifies that this is a supernova remnant. And indeed, this is coming from that part of the space where the supernova 1987A intensive survey, those images are clustered in this space. You're able to do a more accurate retrieval using this pre-training strategy. So this is transformers for text, for images. Well, what about for particle physics data sets? And of course, there is someone who has written a transformer architecture for particle physics data sets, the PART-T, or particle transformer. And basically has the same structure as what you saw before, a bunch of blocks put together. But also, if you look into the details, what you see is that this architecture has hard-coded particle physics knowledge into it. In some sense, hard-coding the Centaur into it. In fact, you get the better performance in particle physics tasks by putting that domain knowledge in there specifically. And part of the domain knowledge that's being baked in is a knowledge about Lorentz transformations. So if I take a particle, I told you that particles disintegrate. When a particle disintegrates, it disintegrates in a way that conserves energy momentum. But if I take that particle and I accelerate it to higher and higher velocities, then the decay products end up getting collimated. This is called relativistic beaming. And yet the actual fundamental object itself was the same. So the thing that I'm known for before working on machine learning is, and stuff that I worked on when I was here at Berkeley, is that if you take this object and Lorentz boost it so much, then what could have been 2 sprays of particles that would give you 2 jets coming from its decay turn into 1 fat jet that maybe has substructure inside of it. But fundamentally, it's the same object. It just happens to be in a different Lorentz frame. So you'd like to teach the machine something about that. And moreover, you want to teach the machine something about that in a way that, if you want to take advantage of this transformer architecture, is a way that allows you to do dot product detention. Basically, you can do this with multiplication. And we need a principal way to multiply particles. And that's also something that we know how to do. This is something that we know how to do, and it is the most loathed part of any class on quantum mechanics. People know this as addition of angular momentum. And this is something that students really hate. They really hate learning about Clebsch-Gordon maps. And you can imagine the challenge of turning Clebsch-Gordon maps and putting that into a transformer. Of course, it's been done. People have done things along those lines. But the basic idea in the language of machine learning is that you want to build equivariant neural networks. You want to build networks such that if I take the inputs, in that case, those jets, and I perform a Lorentz boost, that's the same thing as first analyzing the original object and doing the Lorentz boost after the fact. And, you know, this is 2 things that people have talked about before, but we want to figure out a way to do it in an efficient, computationally efficient and straightforward way. And that's where this kind of Centaur approach comes in. How would I, as a particle physicist, think about encoding information in a way for which this multiplication operation that you need ends up being relatively straightforward? And the answer comes from left field. Okay? And this is a case where actually different people's knowledge in different domains, it's really interesting to see how things that are very natural for me or things that are very natural for you could actually inspire different computational structures. So the thing that's very natural for me, and the thing that I used to work on when I was a grad student before coming to Berkeley as a postdoc, I worked on supersymmetric quantum field theories, which does not seem at all related to what I'm talking about here. In fact, last semester, my students convinced me to reteach the class on supersymmetric quantum field theories, which was interesting. Supersymmetry is maybe not the first thing that graduate students in 2025 would want to learn, but anyway, they wanted me to teach it. And there's a really interesting connection between supersymmetric quantum field theories and building transformer architectures that have built-in ways of doing multiplication consistent with the Lorentz group. May not be obvious to you. The analog is that when we do supersymmetry, we have the same problem in supersymmetry. We have the same problem of having to deal with multiplying objects, but we want to do it in a way that's consistent with this higher symmetry structure. So supersymmetry is a hypothetical symmetry that relates bosons and fermions. These are different types of particles. Roughly speaking, bosons are force carriers, like the W and Z boson and photon. Fermions are matter particles, like quarks. And this hypothetical symmetry relates bosons and fermions, packages them together. But that packaging together is complicated. Well, let's package them together in an object, this thing called superspace. Right, the object itself is called a superfield, but the thing we're gonna use to do that packaging is called superspace, and it's the easiest way to do supersymmetric calculations. So bosons and fermions are very, very different objects. Bosons all want to live in the same quantum state. Fermions definitely do not want to be in the same quantum state. How do you put them together, even though they have different transformation properties or different? Right, and the way you do it is you build a superfield that's bosonic in its core, but you can add in fermionic degrees of freedom because you have placeholders, these theta objects that I teach my students about. And this placeholder allows you to put together things that look like they have different transformation properties, but put them into an object that you can freely add, multiply, in certain cases even divide, and always come back to the same form. And so this is what I teach in my supersymmetry class. We learn about these placeholder degrees of freedom. And the placeholders themselves have the well-divided transformation properties such that at the end of the day, you just use those superfields directly and don't have to worry about the internals. It's done for you directly. So we can do the same thing now, but not with superspace. We now want to do this with Lorentz transformations. And with Lorentz transformations, we have a bunch of objects that have different transformation properties under Lorentz boosts. So the object has a name in the literature. It's called a geometric algebra. You can think about it like a superspace for vectors. And one way of thinking about it is, what is a placeholder that can store information about the Lorentz group such that you can freely add, subtract, multiply, and divide. And the object turns out to come from, in Physicists, we would call these gamma matrices. These are 4x4 matrices that are basically absorb the transformation properties of objects, the way they transform under Lorentz symmetries, and they get packaged together into some object that you can more easily manipulate. So scalars are objects that don't change under Lorentz boosts. Vectors are objects that, for example, under rotation will move. You have antisymmetric tensors, axial vectors, pseudoscalars, a flip sign when you do look at things in the mirror. Those things can all be packaged together into one object that contains the, technically SO3, 1 representations that are most relevant for collider physics. And these are just 4x4 matrices that have well-defined multiplication rules, and you just drop them into a transformer architecture. And so here are the rules on the bottom here, and that's it. Right? So you basically take an existing machine learning architecture that has certain manipulations, you put in a way of packaging together things with more complicated physics-inspired structures, and then everywhere you saw a matrix multiplication, you just replace it by a bigger type of multiplication that includes this additional structure. And so this is a really fun collaboration with folks who are at Qualcomm AI, folks who are at Heidelberg University, and then also Wei Lin here, who was the developer of the particle transformer that I told you about before. And Wei Lin is very happy to have something that's a more principled way, as opposed to hand baking in the domain knowledge from the field. And then, then for the experts, it does really, really well. So this architecture is called the Lorentz-equivariant geometric algebra transformer, or alligator. That's why we have this green alligator logo. And all the green curves here, they are in the direction of doing better on some various LHC analysis tasks. So based on what I've told you on this talk thus far about identifying jets and trying to understand where they come from, this architecture does the best in terms of rejecting jets that are not, in this case, coming from the decay of a top quark. Excellent performance across the LHC pipeline. But the thing I want to emphasize here is this kind of combining of computational structures, getting the state-of-the results, or results from the Centaur style merging of physical structures and computational structures. The physical structure of understanding the symmetries, and the computational structure from this empirical scaling that you see with transformers. Okay, so that was one example, an example that makes particle physicists feel good because like, oh, great, you're putting in something that I know and love. You're talking about supersymmetry, you're talking about gamma matrices, you're putting that into machine learning. That makes us feel warm and fuzzy. And the last part of the talk is the stuff that we have to admit that maybe we need to have the arrow going the other direction and actually learn about the way that machines would process information. And this maybe makes people feel a little bit less warm and fuzzy on the particle side, but hopefully very warm and fuzzy when it comes to the information theoretic or computational side. Okay, so I'm going to start this off by relating to you what I just said about the anxiety maybe that scientists feel when I tell them about trying to think more like a machine, think more in terms of computational structures. And there's a position paper by David Hogg and Soledad Villar that basically writes, is machine learning good or bad for the natural sciences? Basically arguing that there's a fundamental tension between the machine learning approach and the physical sciences approach. And so let me not try to read out this abstract. Let me just give you the kind of summary version of Hogg and Villar's argument, and maybe give you a sense for why actually incorporating more machine-like structures makes us feel queasy. So from the machine learning side, what exists? What are we playing with? What is kind of the fundamental thing? The fundamental thing is data. You get data, you want to process that data. That is kind of the thing that exists. And what does success mean? Success means that I've done accurate modeling of that data. So for example, if I get sample data from the internet and I want to say what does success look like, I can use that sample data from the internet, build a transformer, build a chatbot that mimics the style, for better or for worse, on the internet, or the knowledge that's on the internet. That's what accurate modeling of text would look like. But if you're a natural scientist, there's plenty of things that we think of as existing, even if they're not manifest in data. Going back to the beginning of my talk, quarks and gluons, I think about those as existing. But as I explained to you, they don't really exist in the data sense of that word. They exist as objects or abstract objects in a quantum field theory that I only can infer their existence by doing some type of statistical test. So we believe in latent structures, hidden structures. We think that those things exist. And what is success? Accurate modeling, well, okay, if you model my system, that's not really what I want. I actually want to understand what's going on. And so actually I'm willing to sacrifice accurate modeling if I can actually get a better understanding of the physical principles at play. And so Hogg and Villar basically say that these things are in tension with each other, and they are correct. But in the spirit of being a Centaur scientist, I want to get the best of both of these columns and trying to find an approach that has a little bit of both in it. So let me.
Structures are really important in machine learning, though. I mean, I think all machine learning people would say when you're finding latent structure, isn't it?
So this is one of the excellent complaints about what they're doing, is that when people talk about machine learning, in particular interpretable machine learning, there is this desire to understand what's going on and actually find interpretable internal structures. Yeah. That's right. And so that's one complaint about this paper, is that they've actually, in some sense, cartoonified it too much, and they're saying that accurate modeling is the right thing. But for example, if you're thinking about like out of domain extrapolation, having the latent structure is actually what gives you confidence that you can do that. And so here they're really taking a view of machine learning that is not fair. Also, they're taking a view of the natural sciences that are not fair. And in particular, I wrote an email to David saying, simulation-based inference, where does that fit in there? Because with simulation-based inference, actually the goal is to accurately model the likelihood ratio based on simulation. But we're going to use it in an inference way to get an understanding. So I think this dichotomy is too extreme. And it says these philosophies are in strong conflict with standard practices and key philosophies in the natural sciences and vice versa. I think that's too extreme. And so in some sense, maybe I'm centaurifying this, but actually if you think about where machine learning is going, it's going much more in understanding. And they wrote, well, they didn't write that long ago. But you can complain with David more than with me, because I agree with you in some sense on both sides. I agree with you that there's something to be learned from both of these perspectives. So let me just do the straw man version of this. So the straw man version of this is building a generative model to mimic the LHC. What if you could generate synthetic LHC collisions that were indistinguishable from real LHC data? Okay, so collisions happen every 25 nanoseconds. What if every 25 nanoseconds I could just hit a button and get collisions that looked identical to the ones that we see at the LHC? And people have even kind of thought about whether you could do that in practice. But according to Haag and Villar, this would conflict with the epistemology of the natural sciences. And indeed, I'm not quite sure how useful it would be if I could have that. Because what would I do with that? Great, I can mimic the data, but I can't use that for statistical inference. On the other hand, you could say, what if you could generate synthetic LHC collisions based entirely on first principles quantum field theory calculations? In some sense, this is a grand goal. If you want to think about what I, as a theoretical physicist, would like to do, I would like to be able to take the equations of the standard model and be able to predict where every single pion and can was going to go in a collision event. We are nowhere near being able to do it. It would be amazing if you had it. When I give this talk tomorrow, this is in fact the starting point for that talk, is to say that this is actually what we want to do. To what extent can we do better quantum field theory calculations? But the Centaur Science's approach would be to say, okay, do both things at the same time. Combine models of LHC data that might be hallucinating what the collision debris would look like. They could be incorrect. They could have all sorts of uncertainties or biases. But combine that with full predictions, full phase space, combine those predictions that are over all of phase space, they really look like LHC collisions, combine that with first principles predictions from quantum field theory, whenever those are available. Okay? And then you can ask the question, how can you do that combination? Yes?
So I don't think the first part is possible. I agree with that, but I'm a bit confused. Like, if it were possible, that would be amazing because you don't need LHC high Lumi anymore, right? Just run the simulation, accumulate enough luminosity. You don't need to do anything, right?
Like, I mean, so then I think the reason why I say that that's not useful is that statistical inference requires you to have more than one hypothesis, right? You need to be able to compare, is this the more likely structure of the universe? Is this the more likely structure? So if I just have LHC data, and that's all I have, or a surrogate version of that, and that's all I have, that's not useful. Now, if I could generate synthetic data for also alternative hypotheses, right? But then I need to compare that to something that is the ground truth. So really, yeah, okay, you agree with me. So it's not about, you can't do data analysis if you just have the data. In simulation-based inference, you also need to have data from the alternatives in order to make a determination about latent structures in the universe. That's what I would argue. Okay, so again, Centaur Science, we're going to put these things together. And so let's actually build the Centaur. And as I previewed already earlier in this talk, the inspiration is going to come from.
I have a question on what you last said.
Yes.
Because I could actually try a slightly different thing. I could say, okay, we have this standard model and it's a null hypothesis.
Yes.
And you could actually, if you were really good in your simulation and data analysis, could reject the null hypothesis and say there must be something behind the standard model.
I still need 2 data sets for that. I need to have, or at least I need to have an analytic likelihood for the standard model and then a data set.
Yes.
So if I had an analytic likelihood for the standard model and then I had that surrogate data set, yes, then I could do that. You're absolutely correct. But I need 2 things. Now, I don't have the analytic model, nor do I even have the ability to generate samples from that analytic model. So I have neither of those things. But you're correct. I could reject the null, absolutely. But I mean, the point being made before about could I avoid having to high luminosity LHC is 10 times more data. Can I extrapolate to that 10 times more data just by seeing a subset? I think we would say that you can't really do that, at least not in a way where you could claim any additional statistical significance. Right. Yes, was there a, yeah. Yes. 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 I'm saying something trivial, which is why Haag and Villar would say that this is not useful. And yet, the reason why people would be chasing this is because you're trying to do a comparison of real data to synthetic data. But my synthetic data, the thing that I can actually generate synthetic collisions for, is very limited in what I can predict. And so that's the tension, is that I can generate synthetic data that's not actually realistic. That I can do. I can imagine hallucinating what the LHC data could look like. But if I actually want to do inference, I would like to combine it with first principles calculations. And that's the tension, indeed, something that I worked on when I was a postdoc. So how are we going to do this? We're going to take inspiration from Boltzmann mechanics, in particular Boltzmann machines. And Boltzmann machines are generative models that sample according to a statistical distribution. And so I start off with a Hamiltonian or an energy that depends on the configurations of spins on some lattice. And I learn parameters in order to generate samples such that when I sample according to a Boltzmann factor, I generate samples that agree with, I generate samples that look at like the data set that I'm trying to mimic. And where does this Boltzmann factor come from? This Boltzmann factor comes from finding a maximum entropy solution subject to some type of constraints in this case on the average energy. So when you see e to the minus E over t, E, the thing that appears to a physicist in this Boltzmann factor, that's a thing that I have knowledge of. I have knowledge about the average energy of the system that I'm trying to mimic. So taking this idea of generative models subject to some type of constraints, in this case, constraints on energy, and going from spins to the actual data sets, data structures that we have in particle physics, which are more continuous, we go from maximum entropy to this, what we said before, the KL divergence maximum relative entropy. And what you have for your optimization here, that is generative modeling according to some relative entropy, relative to what? Relative to some prior expectation about what's going on. Subject to constraints, exponential of the generalization of this e to the minus energy over temperature, where these betas are Lagrange multipliers to a physicist that are imposing the constraint, and then the constrained quantity of interest. And this formula is a Centaur formula as written, because I can imagine that this prior knowledge about what collisions might look like at the LHC could come from some hallucinating AI chatbot. Okay, that's fine. But I can constrain it using precision information that's been calculated, the analog of saying I just know something about the average energy. Well, I know something about maybe a limited information from my particle physics calculation. And I can put those two things together. Okay? So this is something that I can do. I can basically build a kind of Boltzmann machine in the continuous limit that has certain constraints in it. You can ask whether that's useful at all for QCD theory, and this is what I'll talk about tomorrow a little bit more, is like, does that even make sense with the structure of QCD calculations? And the answer actually turns out to be yes, that if I look at a random QCD calculation, it has exponential factors in there. It already kind of wants to be like a Boltzmann machine. And it just happens to be that these exponential factors are not called Boltzmann factors. In particle theory, we call them Sudakov form factors. The Sudakov form factors are not constraints on average energy. They're constraints on whatever this L plus B squared is, some kind of logarithmic structure that's being constrained. And so this formula here, if you only looked at it from the lens of QCD theory, you would say, ah, yes, this is a calculation performed to some accuracy. It's so-called next to leading logarithmic accuracy. If you're a machine learning practitioner and you look at this formula, then you say, oh, maybe I see these like gamma functions and Euler gammas. Maybe I could try to use neural symbolic learning to learn the structure. But to a Centaur scientist who has gone to the train of logic that I just gave you, you would look at this formula in two lights. On the one hand, the Sudakov form factor, you have that exponential structure, e to the minus something. That looks like a kind of Boltzmann factor. And then the structures here, the cusp anomalous dimension from the QCD side looks like a Lagrange multiplier from the information theory side. And this enforces a constraint on what? A constraint on the second logarithmic moment of this distribution. Which, okay, now I'm just giving you jargon words, but that realization is the light bulb going off and saying we can actually turn this into an engine to make computations. And so that's what we did. We did the calculation for the first time of these logarithmic moments. This is the first principles information. We then combined it with priors coming from some imperfect generators of synthetic data. And those imperfect generators are shown here as this blue band here, which have large uncertainties coming from not knowing really how the generator should respond. And as you add in some of this information, you can squeeze down the uncertainties in a way that gives you confidence in the result that you're obtaining, and confidence in a way that a particle physicist would understand. So a particle physicist would say, great, you do this thing, compare to data. Yes, we can compare to archival data, and you see the error bars shrinking to the correct answer as measured in data. Oh, no, but you're doing this in one region of phase space. Show me projections in other regions of phase space. Okay, we're going to do a projection to another region of phase space where my one calculation actually has ability to transfer over to another area. And there you see the error bar shrink. And say, oh, no, but you're making the error bar shrink in places where maybe it's not appropriate. No. In cases where the thing that I've done the calculation is not aligned with the thing that I'm trying to analyze, you see the error bars don't shrink. So it doesn't try to make predictions in regions of phase space that it doesn't have access to. So again, this kind of Centaur construction, you're taking advantage of machine learning in various ways, but taking advantage of prior information to cover the whole phase space, and then precision calculations to provide constraints in a way that then you can feed into analyses and hand an experimentalist these type of theory predictions that have information from both areas.
Can I ask a physics question?
Yes.
Here? So when you say QCD, are you talking about ultraviolet or infrared area? I'm talking about the area where I have quarks and gluons which confine, and I want to understand this non-perturbative effect, or are you talking about the region where you have asymptotic field?
I am talking about both. So this is the wild thing about when someone tells you, please compute these logarithmic moments, and you say, that's the thing that I want you to compute. You are forced to confront the totality of QCD, both in the perturbative and non-perturbative regimes. And it's really exciting to work with QCD experts. So it's Ben Ossi, Kyle Lee, and Stefan Höcke to actually figure out how do you do that type of synthesis of non-perturbative and perturbative information in this calculation. And so these error bars actually are coming from a combination of uncertainties on the perturbative side and uncertainties on the non-perturbative side. So it's actually forcing us to think very, very hard about what we're doing, and in a way that we are forced to have theoretical control. So the answer to your question is yes.
Without doing any lattice QCD or so.
Good. What this forces us to do is it forces us to be honest about what we don't know. You're correct. We're not doing a lattice QCD calculation, so we're modeling the non-perturbative physics, and we have to have uncertainties associated with that modeling. So there's uncertainty. There's like multiple layers of uncertainties. There's uncertainties from the modeling of the whole phase space, which I don't have information about. Then there's uncertainties coming from the fact that my theory calculation itself has uncertainties, and then you have to propagate those all together in order to make these error bands. And because I'm working with Stefan in particular, who is very obsessed about making sure these things have the right properties, that gives me confidence that we've at least, as a proof of concept level, done this correctly. But you're asking exactly the right question. And then then it becomes an interesting QCD question about, well, what actually do you calculate? What do you actually have theory control over? And what types of things should you incorporate? What are the things that you constrain? And that ends up being a physics question. Yes, Simon.
What is the use of constrain
Yeah, good. So the way that I told the story was one that was assuming that I had some hallucinating AI chatbot. Okay, what we're actually doing is you are taking Stefan's code of the Dyer shower with his hadronization model, and then what you're doing to generate hallucinations is you're taking that model and you're varying the parameters in that model. So you're saying, I don't know whether it's this model or this other model. You can imagine doing the same thing by just training on the data directly as the thing that you would use, but here we're actually using a generator underneath it. But at the end of the day, we're only using that simulation as a way of generating a prior, and then the calculations are being done with it's related to Ian Stewart's calculations of thrust that he's done. That may not have answered your question. Yeah. So when I talk about this tomorrow, I'll talk about it in the language of parton shower matrix element matching, which is the language that you would be familiar with. And the parton shower is the hallucinating chatbot, and the matrix element are the first principles calculations. Okay, so we're over time. My apologies, but I really appreciate the questions and engagement. Let me leave my summary slide and take any further questions. Thanks so much, and yeah.
Thank you very much for this very comprehensive and fascinating talks. I think we can, depending on people, I mean, if you lead, but I think we can take 2 questions.
I myself have 2 questions.
users.
Then you have to condense it down to 100.
Thanks very much. This is a great talk. So on the second part, you say that you're building the physics principle into the transformer. But you say that if you have sufficiently large training sample, then this will be learned.
Good. Okay. So the question was, well, I'll translate your question. So this is a general question about equivariant machine learning. What would you rather do? Would you rather build in equivariant architectures where the symmetries are baked in, or just have augmented data sets that allow you to learn the symmetry? And specifically for Lorentz transformation, as far as I can tell, it's better to bake it in for the following reason. One of the most basic objects that you want to build as an invariant is the mass of a particle. So the mass of a particle comes from taking the energy and the momentum, squaring both of them and taking the difference. When you take the difference of, let's say, two large numbers when you do a large Lorentz series, taking the difference, getting that right to get the right mass value is a really painful operation to do. So if you tried to learn that, you actually need a very large amount of data in order to actually learn that mass is an interesting object. So whereas with compact symmetries, this is less of an issue. For non-compact symmetries, you can be in a situation that's really hard to learn that structure, which is why baking in the symmetry seems to be particularly helpful in this case.
It's much faster.
But even if you think about the amount of, it's well, faster to train the model, but also it's intrinsically difficult to learn the structure that you're trying to learn because it comes from a difference of two large quantities.
So I don't remember the exact quote, but in November 2020, we were saying that in 5 to 10 years, it is not impossible that there would be a machine learning thingy that finds the theory of everything. Would you still say that in 7 months to 5 years and 7 months? It is
No.
possible that
It's right. So right now, I don't have it on the slide, but you can now take this question and what did I ask? I think I asked 4.0 what its answer would be, and it gave an incredibly sophisticated answer, explaining all of the challenges that you would have to do it, because there's questions of, well, is the actual theory of everything, is it already extrapolatable from the existing knowledge that's on the internet? What types of leaps of judgment would you need? How does this dovetail with experimentation? Because ultimately it's actually experiments that care. And so it gave me this really long explanation about why it was not confident in its own ability to answer that question. So it's not that we're going to get